Hello, physics students, and welcome to our Unit 4, all about work, energy, and momentum. We're going to start this unit by looking at work, what the scientific definition is of work, how work is related to force and displacement, when work is being done in different situations, and how to calculate net work. So there are definitely some different ideas about doing work. We generally think of doing work as expending any amount of energy on some task. We would think that this student is doing a lot of work. But in the scientific definition of work, this student is actually doing no work at all. In fact, in science, work is simply force applied through a distance. Work equals force with the dot product times distance. Force times distance means that if no displacement is happening, we cannot have work being done. So when we look at this situation where this person is exerting a tremendous amount of force, very, very large force, you'd think there'd be very, very large work, but this brick wall doesn't move a bit. Therefore, zero work is done because the displacement is zero, no matter how much force is being applied. So when we have force, this man is exerting a force in this direction, and we have the displacement or the motion of the cart in that direction as well, the very maximum amount of work is going to be done. And you know this just logically. When he's applying the force this way and the displacement of the cart is in the same direction, you're going to get the maximum amount of work that can be done in that situation. But what if those two things are not parallel? What if the force applied is different from the displacement? Such as if he applies a force in this direction and the displacement of the cart is in the horizontal, how do we think about the amount of work done? Well, when the force on the object and the object's displacement are not parallel, only the component of force in the direction of the object's displacement does work. And let's look at an example to understand that better. Here we have a force being applied in this direction, which is 30 degrees above the horizontal. We have the motion of the object, the displacement of the object is perfectly horizontal in this direction. Since only the component of the force in the direction of the object's displacement does work, only the force in the x direction, the component of this force in the x direction will be able to be part of our work equation. So let's solve this little problem. How much work is being done in this situation? I went ahead and labeled the x component of the force. This is the force in the x direction because this is the direction in which the displacement is occurring. So we would like to find the x component of that force. So label this f sub x, and if we think about this as that'll be our right angle right there. We know the cosine of theta is going to be equal to adjacent over hypotenuse, so the cosine of 30 degrees is equal to f sub x, the force in the x direction, divided by 50 newtons for the hypotenuse. When we plug those numbers into our calculator, we get the force in the x direction as 43 newtons. Now we can calculate work because we know work equals force applied through a distance. We know our force in that same direction of our displacement. It's 43 newtons, so we can just plug our values in. And we end up, when we multiply these out, we get 1,300 joules. And we're going to round to only 2 sig figs because that's all we have in our problem. So we have 1,300 joules of work being done here. The units of work are joules. So that may or may not be familiar to you. A joule is a Newton meter. When you look at these units, Newton meter ends up being a joule. Remember that a Newton is a kilogram meter per second squared, And a kilogram meter per second squared is a joule, just like a Newton meter is a joule. So joules are also the unit that we're going to end up using to measure energy. So we have a very handy little formula, and it works so nicely all the time. The net work that is done is equal to the net force times the displacement times cosine theta. And this is true. We can plug those values in and you'll see we get the same answers. So when we plug those values in, you can see that we get the same answer, 1300 joules. So this works very nicely for trying to calculate the component of the force in the same direction as the displacement. We can use this formula each time, and it works. You don't have to rethink the component, but it is this exact same thing. So you can also derive this equation in other ways as well. Way to think of that is that the net work equals the net force times the displacement times the cosine of the angle between that force and that displacement. So let's apply this to a situation where we have the displacement perpendicular to the force. Here the force, his force is holding these books up. If he is walking, his displacement would be going at an angle that is 90 degrees to the direction of the force, directly perpendicular. So what happens in this case? What is the work being done when he's walking around holding these books up with that force, and he's walking about with his displacement perpendicular to it? Remember our formula, our net work is equal to the net force times the displacement times the cosine of the angle between them. I want you to look carefully at that angle. That angle is 90 degrees. When you take the cosine of 90 degrees, you get 0. The cosine of 90 degrees equals 0. Therefore, your net work will be 0 because the angle between them is 90 degrees. So whenever the displacement and the force have a 90-degree angle in between them, in other words, if the force applied is at a 90-degree angle to the displacement, 0 work is done in those cases. And you know this, if you were to push on a cart, the man pushing the cart, if he were to push directly down at an angle that is 90 degrees to the motion that the object is to be doing, there is no work that will be done then. Now let's just look at our equation and understand that when force and displacement are parallel, why is it that we end up with the maximum amount of work? When we have our force, and here this is the direction of the force and this is the direction of the displacement, our angle in between those is 0 degrees. And the cosine of the cosine of theta in this case of 0 degrees, not of theta, when theta is 0, the cosine of 0 equals 1. So we get our absolute maximum amount of work that can happen here. It's just simply force times distance, because the cosine of theta will be 1. In the case where we have a force being applied and the distance is in the opposite direction, that would be the cosine of 180 degrees, because the distance between those is 180 degrees, and in that case, that would be a -1. So in that case, it is going to have to do with the direction of the force, and it will be in the opposite, the displacement will be in the opposite direction of the force, but we will get maximum amount of work. The negative sign will just be an indication that the force applied and the displacement are in opposite directions. So just a little review. You can check your work when you're, you can check your work on work. Does your answer for work make sense? Well, you know that if the force applied and the direction of the displacement are perpendicular, that work is 0. You know that if the force applied and the direction of the displacement are parallel, you know that that's the maximum amount of work. It might be a positive number or a negative number, but it's the maximum amount of work. So you know that when you're making a calculation, you can quickly do in your head an estimation of, does my calculation make sense? Is this number in between 0 and 1, or 0 and -1 in the case where the displacement would be in the opposite direction of the force? And that would give you a very good indication of whether your calculation is in the ballpark or not. Work is scalar. So when we have a vector and the dot product of a vector times a vector is a scalar. And work is a scalar. If you think about it, work does not have a direction. It can be positive or negative, but it does not have a specific direction. Here we just have a little chart helping us think about when the symbol for work would be negative or when it would be positive. If we can think about these cars as this one having a little string here, that there's a force being applied in this direction, and maybe here's a little string here and the force is being applied in this direction. And the motion of the car is in this direction. In each circumstance, the motion of the car is from left to right. Here, let's say we have a hand pushing on the car in that direction, or a hand pushing on the car in that direction. We can see 4 different situations where we're getting either positive values for work or negative values for work. In both of these situations, the force is opposing the direction of the motion. Here we have the components of force are in opposition to the direction of the motion, and here as well. The component of the force is this direction. The displacement is this direction in the horizontal. So both of these situations are going to have a negative value for work because the force is in it. The component of the force in the horizontal is in the direction that's opposing the motion. Here, in these situations, the component of force that is in the horizontal, which is where the displacement is occurring, are going to be in the same direction as the displacement. Here we have the component of force in this direction and the displacement in this direction. Here we have a component of force in this direction and the displacement in this direction. So our sign on the work will be positive. So that is another thing to keep in mind. In addition, remember that force equals mass times acceleration. So in a situation where the work done on an object results only in a change in that object's speed, the sign on the value of the work can be an indication of whether that object is speeding up or slowing down. Because remember, we can have positive acceleration when an object is speeding up to give us a positive value for the force, or we can have negative acceleration where the object is slowing down. That gives us a negative value for the force. Advanced ideas. Try creating your own problems with some of these. Come up with your own, and I look forward to seeing what you have in class.